Today I'm going to talk about a research study on photosynthesis that we have reviewed. Before we start, I would like to introduce my group member. Now, let's move to the purpose of the study. This research is a collaboration between the Indian Institute of Science and the California Institute of Technology. It uncovered new insight into photosystem 2, which play a critical role in the right-dependent reactions of photosynthesis. The main focus of the study is to understand why electron transform happen only through the D1 times of photosystem 2. Every through D1 and D2 have nearly identical structure. Understanding this mechanical can help scientists design artificial photosynthesis and develop cleaner, more efficient solar energy system. To better understand the purpose of this study, let me first explain photosystem 2. PS2 is a protein pigment complex in the choroplast that split water molecules using sunlight. It contains two branches, D1 and D2, both of which could internally transport electrons. Interestingly, in natural, electron transform occur only through the D1 time. The pathway follows chlorophyll to phosphatin to prostaglandin, and this process is fundamental for transforming solar energy into chemical energy.
Why D2 doesn't function like D1? Even though D1 and D2 are structurally symmetric, D2 is actually inactive in electron transfer. According to quantum calculation and Mercator's theory, D2 faces a much higher energy barrier. Because of this, electron flow through D2 is about 100 times less light compared to D1. So even though D2 is present, nature seems to have optimized only D1 for the specific function. Molecular and environmental difference. Researchers also study the microenvironment around the chlorophyll molecule in both arms. In D1, the energy levels are lower, which stabilize the chlorophyll and make electron transfer easier. Water molecule and nearby amino acids features support this process. In contrast, D2 have higher local energy state, which makes it much harder of electron to transfer. This key difference explains why nature chose D1, even though both arms look symmetrical in structure.
Regarding D2, a theoretical fit, the team proposed an engineering solution swap the position of chlorophyll and phosphatin in the D2 arm. This could reduce the energy barrier, allowing D2 to support electron flow like D1. This approach could number the efficiency of electron transport in the artificial system. If successful, this method could open up new ways to design energy harvesting technology. Implication for solar energy and technology. Artificial photosynthesis aim to mimic plants to convert sunlight into clean fuel or electricity, reduce reliance on fossil fuel. This research gives insight into how to optimize synthetic light harvesting system. Potential application: artificial leaves, solar fuel generation, biohybrid solar panel, a key step toward sustainable energy future by learning from millions of years in evolution.
Expert commentary on future outlook. Professor Kawasaki rating IISc. NASA have optimized photosystem 1 PSI2 at extraordinary level. This study explains how and why its function so efficiently. Professor William Gordon Carter. The research are exciting and hold great potential for breakthroughs, but applying them in the level will require more time development. Future work design artificial system with D1, D2 energy pathways. Test energy transfer model in lab genus protein. These lab results are major step forward in understanding both biology and renewable energy. Thank you.